Alrighty, so good morning, everybody. I hope you guys had a great weekend and that Monday went all right. And that you're feeling good today, ready to learn. We have the last section of chapter 8 that we're gonna get through today, as far as like the lesson lecture kind of thing. It is section 8.3 on estimating a population mean. A lot of the math and strategies we're going to use today are very similar to what we did last week with estimating a population proportion. The formula's changed just a little bit, but it's the same concepts, right? So we're building off of what we've been doing and taking the next step, all right? I recommend that you have something that you can take notes on. There will be a few things that you should write down. Again, you shouldn't be writing down everything on all the slides. Some of these slides are just kind of to move us forward to the main concept that we need. When there's things that I think you need to write down, I will say you should probably write this down in your notes. We're going to get through the presentation, and that will have some examples of the things that we're going to do today, and then I also do have a couple of sample problems to work through with you guys as well, kind of like what I did last week with the proportions. All right, so that's kind of the idea for today. As usual, if you have questions, if I'm going too fast, if you need clarification, please let me know. Obviously, I will pause to ask if people have questions or if you need time to write things down. But if I'm missing it, please let me know. Raise your hand, shout at me, type in the chat, any of those things all work. All right, so we're gonna get started. Alrighty, so here we are, chapter 8, estimating a estimating with confidence, estimating a population proportion. We're gonna get going. So today, right, the goal here is that we will be able to state and check the random 10% and normal large sample conditions for constructing a confidence interval for a population proportion. Notice the first two things are the same as when we were doing a population proportion. Now we're doing a mean, random 10%. Those things are still existing. And then we have the normal large sample, which is akin to the central limit theorem from last chapter, saying that when our sample is at least 30, we can do normal calculations and treat this as a normal curve. We're going to be able to explain how the t distributions are different from the standard normal distribution and why it is necessary to use a t distribution when calculating a confidence interval for a population mean. We'll get to that one. We're going to be able to determine critical values for calculating a C% confidence interval for population mean using a table or technology. We can construct and interpret a confidence interval for a population mean and determine the sample size required to obtain a C% confidence interval for a population mean with a specified margin of error. Right, the last three things here is essentially the same type of work we did with our proportions. We're now doing it with means. So first, when sigma, right, our standard deviation is unknown, we use the t distributions. Right, when the sampling distribution of x bar is close to normal, we can find probabilities involving x bar by standardizing. This is what we've done previously. Right, we have our sampling distribution of x bar, we standardize it, and we get our standard normal curve with a standard deviation of 1 and a mean of 0. That's what standardizing does. When we don't know sigma, we can estimate it using the sample standard deviation S sub x. What happens when we standardize? Right, we now have S sub x here instead of sigma. Right, we still have x bar minus mu, square root of the sample size, right? What happens? When we standardize based on the sample standard deviation S sub x, our statistic has a new distribution called a t-distribution. It has a different shape than the standard normal curve. It is symmetric with a single peak at 0. However, it has much more area in the tails. It's not as narrow. Here's an example. We have our t-distribution of x bar minus mu divided by s sub x divided by square root of n. We get this much more spread out distribution as opposed to a standardized score using the standard deviation, a known standard deviation, right? And we get this much more condensed distribution. Like any standardized statistic, t tells us how far x bar is from its mean mu in standard deviation units, right? So just like in our previous section, we used z star, we used z-scores as a critical value for means. When we're estimating population means, we use the t value for our critical value. Right? There's a different t-distribution for each sample size specified by its degrees of freedom. Right? This will make sense in a moment when we see some examples. So we've got a couple of new things. We've got the t-distribution, which we'll see what this is in a moment, and degrees of freedom. Right? These things are connected. You use them. You use degrees of freedom to find your critical value on a t-distribution, which is another table. It's called table B. We'll get there in a moment. Does anyone need a moment to write anything down? Please raise your hand. Okay. So when we perform inference about a population mean mu using a t-distribution, the appropriate degrees of freedom are found by subtracting 1 from the sample size n, making degrees of freedom df equal n minus 1. We will write the t-distribution with n minus 1 degrees of freedom as t sub n minus 1. So we have conditions for constructing a confidence interval about a population, about a proportion. About a proportion. That should not say about a proportion. It should be about a mean. All right. So draw an SRS of size n from a large population that has a normal distribution with mean mu, standard deviation sigma. The statistic t equals x bar minus mu divided by s sub x divided by square root of n has the t-distribution with degrees of freedom n minus 1. When the population distribution isn't normal, this statistic will have approximately a t sub n minus 1 distribution of the sample size if the sample size is large enough. This is all well and good information. It is not critical that you write this down. Right? You most likely will not have to use this exact formula. It's just so we know where t came from. When comparing the density curves of the standard normal distribution and t-distributions, several facts are apparent. Right, so we have this curve here, the most narrow curve, that's also the most tall curve, is our normal, standard normal curve. The dotted line here represents a t-distribution with 2 degrees of freedom. So it's kind of a little more wide, tails are larger. We have 9 degrees of freedom with this little dot line here. All right. T-distributions have more area in the tails than the standard normal distribution, which is why they're higher here, lower here, right? Still has to be 100% of the area, so they kind of like get smushed down and get longer, fatter. The density curves of the t-distributions are similar in shape to the standard normal curve. Spread of the t-distributions is a bit greater than that of the standard normal distribution. And this, honestly, this makes sense, right? Because when we consider what we know from like sampling distributions, the larger sample size we take, the less variation we get. So this thing gets more narrow. So with a smaller degree of freedom means we had a smaller sample size, meaning we should have more variance. So this is kind of connected to that same concept. The t distributions have more probability in the tails and less in the center than does the standard normal. As the degrees of freedom increase, the t density curve approaches the standard normal curve ever more closely. And again, that relates to the fact that as we get a larger and larger sample size, we get closer and closer to just normal. Is there anything I can clarify so far, or does anyone need a moment to write stuff down? So what we use is called table B. That is our t distributions, and it's how we find critical t star values, similar to these z star values. So we have a problem here. What critical value t star from table B should be used in constructing a confidence interval for the population mean in each of the following settings? So A, we have a 95% confidence interval based on an SRS of size n equals 12. In table B, we consult the row corresponding to degrees of freedom equals 12 minus 1 equals 11. So on table B, there is a column for degrees of freedom. We find 11, right? And then on the bottom of table B, there's the confidence levels. So we'll find 95%, find the intersection of those, and that gives us a t star of 2.201. Right. The top row actually tells us the proportion under the curve greater than the t value on the curve. Right. We'll see. I'll show you a picture of this in a moment. We move across that row to the entry that is directly above 95% confidence interval on the bottom of the chart. The desired critical value is t star equals 2.201. Right, so we use this in a similar fashion that we use table A, and where we can we line these things up and find the intersection. So we just got to practice using it. So we'll do another example here. A 90% confidence interval from a random sample of 48 observations. Right. With 48 observations, we want to find the t star critical value for degrees of freedom 48 minus 1 equals 47 and 90% confidence interval. Notice there is no 47 on table B. This is not because they're just skipping to show less values. It's not listed. There is no degree of freedom 47 row in table B, so we use the more conservative degree of freedom equals 40. Right, we will use, as we can refer to, Price is Right rules, as close as you can get without going over. Right, so that means I can't use 50 even though 50 is closer to 47 because 50 is greater than 47. So we err on the side of caution and be more conservative, and we round to the lower value that's closest to 47, which would be 40. Right, again, I like to think of it as using Price is Right rules as close as you can get without going over. Okay, so the corresponding critical value is t star equals 1.684. Is there any questions on this so far? Anything to clarify about table B on our first sightings of it here? Okay. Conditions for estimating mu. As with proportions, you should check some important conditions before constructing a confidence interval for a population mean. Right? So we have conditions for constructing a confidence interval about a mean. You do want to write these down. Similar to proportions, we have to check 3 things in order to be able to make an inference. Okay, so we must have a random sample. The data came from a well-designed random sample or randomized experiment. The 10% condition must be met. So when sampling without replacement, check that n is less than or equal to 1 over 10 times n. Right? Sample size is less than or equal to 10% of the population. And we have the normal large sample. The population has a normal distribution, or the sample size is large and is greater than or equal to 30. So similar to our previous lessons where we're talking about a sampling distribution, right? If the parent population is normal, then so will the sampling distribution. We don't have to worry about it being large enough. If we don't know if the parent population is normal or the parent population might be skewed, then we need to make sure that the sample size is large enough. If the population distribution has unknown shape and n is less than 30, use a graph of the sample data to assess the normality of the population. Do not use T procedures if the graph shows strong skewness or outliers. Okay. So again, if we don't know what shape the parent population is and the sample size is small, less than 30, then we have to graph the sample data and decide if it is strongly skewed or has like severe outliers. Right? If those things exist, then we cannot use this process. Okay. Now, something to note is if there is skewness or outliers, right? You have to take that step of making a like box plot or a dot plot or something to see the shape of your sample. It will be obvious that it is strongly skewed or there's severe outliers. It will not be a question of maybe it's a little skewed, maybe there's an outlier. It will be apparent. They're not going to trick you with that. Or at least I've been told they're not going to. Does anyone need a moment to write anything down? When the conditions for inference are satisfied, the sampling distribution for x bar has a roughly normal distribution. Because we don't know sigma, we estimate it by the sample standard deviation S sub x. The standard error of the sample mean x bar is S sub x divided by the square root of n. Where S sub x is the sample standard deviation, it describes how far x bar will be from mu on average in repeated SRSs of size n. The standard error of a sample mean is a formula provided on your formula sheet. It's Sx, or I think on the formula sheet it says Sx equals S over square root of n, but it is a provided formula. Need to use it, but it is provided. To construct the confidence interval for mu, we replace the standard deviation of x bar by its standard error in the formula for the one sample z interval for population mean, which we'll see in a moment. Or I'm sorry, which we've already seen, the z interval. Use critical values from the t distribution with n minus 1 degrees of freedom to in place of the z critical values, that is statistic plus or minus critical value times standard deviation of statistic. Same like base for the formula that we use for proportions, right? Our statistic now is x bar, the critical value is t star, and the standard deviation is the standard error for a mean, which is S sub x divided by square root of n. So we're using that same formula base that we used for proportions, whereas proportion was p hat plus or minus z star times the square root of p hat times 1 minus p hat divided by n. Right, so we're using a very similar methodology here to find our interval. So we need a moment to write anything down. So we then have the one sample t interval for a population mean. The one sample t interval for a population mean is similar in both reasoning and computational detail to the one sample z interval for a population proportion. And here it is. This is something you're going to want to write down and get used to when the conditions are met. Random, 10%, normal, large counts, essentially normal, large sample. But a C% confidence interval for the unknown mean mu is x bar plus or minus t star times s of x divided by square root of n, where t star is the critical value for the t n minus 1 distribution with C% of its area between negative t star and t star. The value you find from table B. Does anyone need a moment to write this down? So let's look at an example. Environmentalists, government officials, and vehicle manufacturers are all interested in studying the auto exhaust emissions produced by motor vehicles. Major pollutants in auto exhaust from gasoline engines are hydrocarbons, carbon dioxide, and nitrogen oxides, NOx. Researchers collected data on the NOx or NOx levels in grams per mile for a random sample of 40 light-duty engines of the same type. The mean NOx reading was 1.2675 and the standard deviation was 0.3332. We want to construct and interpret a 95% confidence interval for the mean amount of NOx emitted by light-duty engines of this type. And we will be using our 4-step process, right? State, plan, do, conclude, to make sure we don't skip anything. So state, we want to estimate the true mean amount, mu, of NOx emitted by all light-duty engines of this type at a 95% confidence interval. Plan, if the conditions are met, we should use a one sample t interval to estimate mu. Part of the planning phase is checking conditions. Right? Random, the data came from a random sample of 40 engines from the population of all light-duty engines of this type, so it is random. 10%, we are sampling without replacement, so we need to assume that there are at least 400 light-duty engines of this type. That's a fair assumption. Large sample. We don't know if the population distribution for NOx emissions is normal. Because the sample size is large, n equals 40, which is greater than 30, we should be safe using a t distribution. Right? Our large sample condition has been met. Is there any questions so far? Now we're on to the do step. From the given information, x bar equals 1.2675 grams per mile, and s sub x equals 0.3332 grams per mile. To find the critical value t star, we use the t distribution with degrees of freedom 40 minus 1 equals 39. Again, Price is Right rules. We use 30 on the table. All right. So 30 and, whoops. Sorry, that corresponds to the value of 2.042. Right, we have 30 here, 95% here, 2.042. So we get x bar plus or minus t star s of x divided by square root of n. We get 1.2675 plus or minus 2.042 times 0.3332 divided by square root of 40. We get 1.2675 plus or minus 0.1076, and we get the interval 1.1599 to 1.3751. And we can conclude we are 95% confident that the interval from 1.1599 to 1.3751 grams per mile captures the true mean level of nitrogen oxides emitted by this type of light-duty engine. So it's a lot of the same process that we did with proportions. We're just using a different table. Right? We're not using table A, we're using table B. And essentially the same formula to find our interval. We're getting margin of error. All those same parts are still here. Anything I can clarify about this example? Okay. Similarly to what we did with population proportion, we sometimes need to estimate the sample size or choose a sample size before taking our sample. So choosing sample size for a desired margin of error when estimating mu to determine the sample size n that will yield a level C confidence interval for a population mean with a specified margin of error ME. We need to get a reasonable value for the population standard deviation sigma from an earlier or pilot study. Right. So we hopefully have some idea of what it is for the standard deviation. Find the critical value Z star from a standard normal curve for confidence level C. Notice this now switches back to Z star. All right, so we'll use the same technique as we did with proportions. In, say it was a 95% confidence interval, we find, that leaves 5% split between the two tails. That's 2.5% for one tail. We find the closest value we can, 0.025, no. Yeah, 0.025 on table A. Trace that out, we get 1.96. We've seen that result for 95%, but same idea. All right, set the expression for the margin of error to be less than or equal to margin of error and solve for n. Right, in this case, we just have a lot less things going on, right? We use Z star again, just like we did with proportions, but now the standard error formula is just a little smaller. Right, we have our standard deviation divided by the square root of n. And we rearrange this to solve for n. Right, so the major difference between this and the proportions is with proportions, if I don't have anything to go off of, I just estimate that the population proportion is 0.5. In this case, if I don't have anything to go off of, I can't guess the sample size. Right? We need a reasonable value for the population standard deviation to move forward with this. So that should be provided in our examples, or we have a way of calculating it. Does anyone need a moment to write this part down? So we have an example. So researchers would like to estimate the mean cholesterol level mu of a particular variety of monkey that is often used in laboratory experiments. They would like their estimate to be within 1 milligram per deciliter, mg per dl, of the true value of mu at a 95% confidence level. Previous study involving this variety of monkeys suggests that the standard deviation of cholesterol level is about 5 milligrams per deciliter. Problem. Obtaining monkeys is time-consuming and expensive, so the researchers want to know the minimum number of monkeys they will need to generate a satisfactory estimate. All right, so our solution for a 95% confidence, Z star equals 1.96. We've seen this result several times. We'll use sigma equal 5 as our best guess for the standard deviation of the monkey's cholesterol level. We're going to set the expression for the margin of error to be at most 1 and solve for n. So we get 1.96 times 5 over square root of n is less than or equal to 1. We rearrange, right? Multiply both sides by square root of n, divide both sides by 1, which we don't actually have to divide by 1, but you know, they're showing that step. So we have 1.96 times 5 divided by 1 is less than or equal to n. We square both sides and we get 96.04 is less than or equal to n. In other words, n is greater than or equal to 96.04. Because 96 monkeys would give a slightly larger margin of error than desired, the researchers would need 97 monkeys to estimate the cholesterol levels to their satisfaction. And again, we don't round it down to 96 because n must be greater than 96.04 and 96 is less than 96.04. So we round up to 97 to satisfy the inequality. Are there any questions or is there anything I can explain in better detail or go back to a previous slide? All right. So then that gets us to the end of this presentation. So now we're going to look at an example problem, a couple of example problems, one with calculating and interpreting an interval, a confidence interval, and one with finding a sample size. Right, so we're going to go look at those. Over here. All right. So here we have our first example problem. All right, so we have bone loss by nursing mothers. All right, so breastfeeding mothers secrete calcium into their milk. Some of the calcium may come from their bones, so mothers may lose bone mineral. Researchers measured the percent change in bone mineral content, BMC, of the spines of 47 randomly selected mothers during 3 months of breastfeeding. The mean change in BMC was 3.587%. The standard deviation was 2.506%. All right, so this would be X bar. That's S sub X. All right, we want to construct and interpret a 99% confidence interval to estimate the mean percent change in BMC in the population. Right, and to do this, we're going to use our 4-step process. So step number 1 is state. All right. So we want to estimate actually it's right like this. Mu equaling the true mean percent change in BMC in breastfeeding mothers. All right, so that's what we're going to be doing. We are going to plan. Right, if conditions are met. We will will use the 1 sample t interval for population means. So that's the inference method we're going to use, which then means we need to check things. So we have random 10% and normal slash large sample. We have to check each of these things. The sample was a random selection. So that's satisfied. All right. Our 10% condition, it's reasonable to say that that 47 is less than 10% of the entire population of breastfeeding mothers. All right, so let me just say that 47 is less than 10% of all breastfeeding mothers in our normal large sample. All right, we have, since n equals 47 is greater than or equal to 30, the sample size is large enough. We'll leave it at that. All right, so now that's the entire part of the planning part of this thing. So we can move on to the do phase, which means we got to do some math. All right, so we first consider the degrees of freedom. So our degrees of freedom is equal to 47 minus 1, which equals 46. All right. We're also dealing with a 99% confidence interval, so that's what we're going to find on table B. Right, so let's look at table B. Once again, we have degrees of freedom of 46. 46 does not exist as a degree of freedom on table B. Right. But we can't overestimate at 50, so we will use 40. Right, 99% is here. Right, so we follow this up, and we follow this one over. Right, and we get the intersection here of 2.704. So we use a t star of 2.704, right? And our sample standard deviation and is a value that we got earlier, right? 2.506, and x bar over here. So we need to do our math now. And again, this formula is going to be x bar plus or minus t star times s sub x over square root of n. We'll replace all of our numbers here, all of our variables, so we get negative 3.5 2.87 plus or minus 2.704, and we have 2.506 divided by square root of 47. Right, so this is our calculation for our interval. We get negative, sorry, we put this all through the calculator, we get negative 4.575 and up to negative 2.599. So this produces our interval. So that's the do part. We've done the math, and now we write our conclusion, which we'll put down here. And we get to say we are 99% confident that the interval from negative 4.575 to negative 2.599 captures the true mean percent change in BMC for breastfeeding mothers. So we don't have any questions about how we worked through that 4-step process and constructed our confidence interval and got to our conclusion. Is there anything I can clarify? All right, so then based on our interval from part A, do these data give good evidence that on the average nursing mothers lose bone mineral? Okay, and yes, the short answer is yes. All right, so since we have it there. All the plausible values are negative, indicating bone loss. The data give evidence that breastfeeding mothers lose bone mineral on average. Right. So we're now making an inference, right? Using our data and saying whether or not a claim is supported based on what we've inferred. All right. And our last example here. So we have the SAT. High school students who take the SAT math exam a second time generally score higher than their first try. Past data suggests that the score increase has a standard deviation of about 50 points. How large a sample of high school students would be needed to estimate the mean change in SAT score to within 2 points with a 95% confidence? So for this one, it's best again to start out. Let's just list what we have. What do we know? All right. We have a standard deviation of 50 points. We have a margin of error that we want to be 2 points. We're dealing with a 95% confidence interval. Right, and that gives us a z star of 1.96. Because again, remember when we're trying to guess the sample size or determine a sample size, we use z star instead of t star, even though we're dealing with a population and we're dealing with means. All right, and so with this, I have everything I need to get started. We're going to solve for n, right? We have z star times standard deviation divided by square root of n is less than or equal to the margin of error. We're going to do all of our substitutions here. We have 1.96, right, times 50 over the square root of n is less than or equal to 2. I'm going to multiply each side by the square root of n and divide each side by 2. Right, and that allows the square root of n to cancel on the left-hand side and the 2's to cancel on the right-hand side. Right, we end up with 1.96 times 50 divided by 2 is less than or equal to the square root of n. Square each side to cancel out the square root. And we get, on the left-hand side, 2,401 is less than or equal to n. And we can write down we would need at least 2,401 high school students to estimate the mean change in SAT scores within 2 points with a 95% confidence. And we're done. Is there anything I can clarify about the SAT problem here? Okay. Alrighty. Stop sharing my screen here. All right, so the practice problems for 8.3 are already available in Canvas under the resources for Chapter 8. The solutions are also already available. So if you'd like to get some practice in with these new concepts here for estimating a population mean, those are available. We will also, as our kind of pattern is, we will have a practice activity to practice some of these skills tomorrow in class. So, be here to get in that practice and get some more learning in and get more familiar with these things. I will have the assessments for Chapter 8 ready hopefully by tomorrow. I'm almost done with multiple choice, and then I've got to put together the FRQ ones. And so that will be forthcoming later this week. And other than that, if you guys have any other questions, anything else I can help you with today, any clarification for today's lesson or previous lessons, please stick around, let me know, or send me a message. Other than that, have a great rest of your day, and I will see you tomorrow.